slide past you here.
You know, the reception's terrible in the math lab.
All right, let's get started. I don't have your take-homes done to hand back. Just didn't have enough time, so I'll have those for you next week. I try and get them done by Friday, so I'll post the grades online. Hopefully you aren't in too much of a hurry to get those grades. On the next mini exam that I handed out last time, I've had some questions about, is it as straightforward as it seems? And it is as straightforward as it seems. But just make sure that since it is very computational and very mechanical, that you are paying attention to your derivatives, double checking your chain rule and things like that, because that's what I'm going to be looking for, accuracy, okay? That's it. We're going to move on. So we're in 11.6 now. We finished up chain rule last class. And this section is entitled The Directional Derivative in the Gradient Vector. So I'm sure you all remember the wonderful demonstration that I did when I got up on the chair, right? And I was trying to point myself in certain directions, right? And what we had basically was a surface, right, a function of two variables. And we said when we're standing up on the surface at a point, we could point in a direction that would be parallel to the x-axis, right? And that slope of that line would be our partial derivative with respect to x. And then we could point parallel to the y-axis, and that would be our partial with respect to y, right? Yes? But we also had kind of talked a little bit about, well, why point that way or this way? There's actually an infinite number of directions I could have pointed, right? And that's what today is about. The directional derivative is a more general version of what we've already done. It allows us to point in any direction as opposed to just parallel to one of the coordinate axes. So to start, we're going to take a look at this visually first. So let's see how this works out. We recognize this is a surface. Can you all kind of see this surface here? Yeah? Okay. And it's actually f of x, y equals sine of x minus y plus cosine x. So there it is. There's that sheet that's floating in the wind, right? Well, it's not moving. It's actually, but the idea is that it's some surface up here. And I'm actually at a point right here. So that's a point up on the top of the sheet. And if I look at this straight down like this, okay, then this is my x-axis, this is my y-axis, z is coming out at us, right? And I want you to notice that below this point, directly below it, down on the domain, right, on the xy plane, I have that red point. And right now that red point is pointing, right? I have this point, I have this arrow, this is pointing down the x-axis, right? So if we were to sit there and ask ourselves to find the slope of the tangent line as we are pointing parallel to that red vector, we'll call it a vector, then what we're doing is we're holding y constant, right? And we're slicing this thing through, creating the curve, and then finding the tangent line, which is this, I don't know if that you can see that, but it's that blue line, right? And that's what that partial derivative, oh, it's not showing up over here. It's okay, don't worry. But that's what that partial with respect to x would be, yeah? Now, if we change it and we run parallel to the y-axis instead, what I'm going to do is I'm going to rotate this vector and point it out to the y, right? So let me do that now. There we go. So I've pointed out the other direction. You all agree? I can slice it the other way and find the tangent. That tangent line isn't showing up very good, but y'all see it? Okay. So let me go back to the other one because it seemed to work better. There it is. Now, today, what we're going to do is we're going to use this arrow and we're going to just rotate it arbitrarily. So let's see what happens if I take that arrow and just start, well, oh, I'm doing the wrong one, sorry. This one. So you see it? See how this spins around like this? And wherever I want to stop it, I can stop it. And once I stop it, I have another graph that's cutting through the curve, and I have another tangent line. So for every direction, I have some tangent line, don't I? And our goal is to try and come up with a way of having a formula that would represent that slope. Got it? No questions on it geometrically? All right, so what are some things I said to look at? We can pick any point in the domain to get a point on the surface. So back to this picture. I was at the origin here, wasn't I? I was at the origin, that's where I was. But I could go to any place. I could go to another place on the surface if I wanted to. All right, so I could go over here, kind of on this front edge of the surface, and I could cut through that with the plane, get the tangent line, and spin that thing around, right? Yeah? So what I want you to see from this view, if I'm spinning this around, that red vector, I didn't move it. So if I look at this from the top, do you notice that my plane, I'm going to rotate a little more. Damn it. There we go. Notice that the plane that's cutting through the surface at this point is parallel to this, right? Okay, so this is a vector. We could imagine you could slide that vector over underneath this. I didn't do that. I could go back into the code and redo it and have it do it, but I just left it at the origin, all right? All right, so we can find this, all right? We can pick any point in the domain to get a point on the surface. At that point on the surface, we can pick any direction we want. In that direction, there is a tangent line. The slope of that tangent line depends on the direction that we're pointing in. That's what we know so far. Where's my formula? I was like, where the hell's the formula? We need the formula. All right, there we go. So here it is. This is the Big Daddy formula for today. And I'm going to write it down on the board over here so that we have it. So I don't have to keep referring back to it. By the way, the homework assignment for last class for the chain rule, I never gave you the homework assignment, but I emailed it to you today. And the homework assignment for this section, I did the videos for the homework today, so they're already up on YouTube. And the assignment for this is at the end of the notes. So this is the formula. Let's talk about this. All right, this capital D tells you that we have a derivative, right? That was one of the notations. So this is the derivative. Right, so if z is a function of x and y, so we've got this surface, then the derivative of the function f of xy in the direction of u. Okay, so this u subscript tells you the direction you're pointed in. Do you remember when we did this notation? Like, we never used it. I showed you all these different notations. But wouldn't this mean, oops, sorry. Sorry. Wouldn't this mean the partial derivative with respect to x? Which means point in the direction parallel to the x-axis, right? So this x actually was telling us the direction. We weren't really looking at it that way. This is telling us the direction is going to be u, which is going to be a vector. It will be equal to a times the partial, this is times the partial of f with respect to x, plus b times the partial of f with respect to y, where a and b are the components of the vector in the direction we're pointing. So we just need to know what direction to point in. But there's one huge thing you have to be careful with. The direction vector that you use for this formula, the u, must be a unit vector. It has to be a unit vector for this formula to work. If it's not a unit vector, then you have to make it a unit vector. And how do we make unit vectors out of vectors? Divided by its length or multiplied by the reciprocal of its length, right? So we know that if someone gives us a direction, we can always find a vector in the same direction with unit length. Now what's really kind of nice about this formula, before I get to this example that's coming, and I'm going to make this smaller now. That's too small. Can you read that? Yeah. Okay, so what's nice about this is what if I gave you a unit vector? Well, you can tell me if this is a unit vector. What if I gave you this direction? So I'm not doing this problem right now, okay? I'm just asking you to think about this. Is that a unit vector? Yes, okay. What direction is that pointed in? So think about domain-wise. If you're just looking at the ground, you know, here's your x, here's your y. This is just the domain of the f function. This is the vector I hat, right? Which just points out to the right. So it's pointing in this direction, like this. And if I'm pointing in that direction, isn't that exactly the partial derivative with respect to x? Well, let's see what happens in our formula. If we go and use that formula over there, do y'all see what's going to happen? What's a for us? 1, so you get what? Partial of f with respect to x at xy plus, now what's b? 0, so 0 times partial of f with respect to y at xy. This is gone, and it's just the partial of f with respect to x, which is what it should be, because I'm pointing in the x direction, yes? Similarly, if I used a different direction vector, like, I don't know, j hat, then I would be pointing down the y-axis, wouldn't I? And it should be, that should correspond to the partial with respect to y, which it would, right? Because this would be 0 now in front, and this would be 1, right? So do you see that this is just a more general formula? In the event that we're pointed down the x-axis, it still works, or the y-axis still works, but it works for all directions. All right. So let's do this problem. If z is equal to f of x, y is equal to x cubed minus 3xy plus 4y squared, then find the directional derivative at the point 1, 2 in the direction of a vector making an angle of pi over 6 with the x-axis. All right. So let me look real quick, at the domain. Here's a domain of f, which is the flat ground, right? That's the ground, just looking at it from the top. So here's x, here's y. I'm going to the point 1, 2, so 1 for x, 2 for y. And that point's getting plugged into the function, right? So three-dimensionally, it looks like this. Here's x, here's y, here's z. Going out 1 on x, 2 on y. So something like that, right? That point. Agreed? That's being plugged into the function, which is sitting, what? It's a surface. It could be below, right? It could be, but let's just, for the sake of making this easier to look at, let's just say that surface is sitting above us, up here somewhere. Here's my little surface up there. And I am plugging this in, and I should be somewhere on this surface, right? Somewhere on there. There's my point. Now what I want to do is I want to point in the direction of a vector making an angle of pi over 6 with the x-axis. So come back over here to this domain. Imagine a vector that starts at the origin and has an angle of pi over 6 with the x-axis. Pi over 6 is 30 degrees. So it's pointed in this direction like that, right? I want to take this point, I want to go up to this function, which means go up to there, and be pointing the same direction as that. Do you all follow that? And then from there, figure out what the slope tangent line is. So that's going to be kind of hard to draw the pi over 6 here, but I think it would look something like this on the ground, wouldn't it? Y'all kind of see that on the ground? Okay, so I just need to come up here to my function, and I need to kind of point in the same direction. Kind of hard to do, too close to the board. I need to point in the same direction as that vector. That doesn't look like the same direction, does it? It's hard to do, but you get the idea, right? And just imagine if I'm standing there pointing in that direction and I take a step, right? Am I going up or down? If I'm going up, by how much? If I'm going down, by how much? And that's what this derivative represents. It's an instantaneous rate of change at that point on the surface. Yeah? Okay. So, it's a directional derivative. So we're going to need to use that formula. Do you think that you'll be able to find the partial of f with respect to x? We'll need that, right? Because it's in the formula. We can do that, partial. We can do the partial of f with respect to y, no problem. All we need to figure out is what's u. What is u? And u has to be a unit vector that points in the same direction as that vector right there, the red one. So how are we going to get u?
Make a vector out of 1 and 2 and then multiply.
Be careful. This 1 and 2 has nothing to do with the direction we're pointing, right? The 1, 2 is just where we are up on the surface, right?
Use trig.
Okay, you can use some trig here, couldn't you? Let me see. I'll leave this up here. How about I use this? How about the unit circle? Don't we love the unit circle? Somewhat. Pi over 6 is right here. And that corresponds to an actual point that we all should kind of remember from pre-cal. This was a common angle, wasn't it? This is root 3 over 2 and 1/2, isn't it? So if I have an angle of pi over 6 with the x-axis, that corresponds to that point on the unit circle. And of course, I can make a vector out of that point, couldn't I? Just turn this into a vector, and that's going to correspond to the direction I want to point, right? So how about that as a candidate for you? How about root 3 over 2, 1/2? Now, it has to have unit length. Is it a unit vector? Well, it came from the unit circle, so it should have length 1. But you could double check it, right? You could just take its magnitude real quick. What's the magnitude of this? Square that. 3/4, square that. 1/4, 3/4 plus 1/4 is 4/4. That's 1, take the square root. So yes, it is a unit vector. Okay, so that's it. We have everything we need. This is A, this is B, and we just go to the formula. Well, we never took the partials. Why don't we take the partials next? I'm trying to preserve as much room as I can up here. Let me do the partials right here. What is the partial derivative of f with respect to x? 3x squared minus 3y, and that's it, right? Yes? All right, so 3x squared minus 3y, and then the partial of f with respect to y, which is minus 3x plus 8y, right? So that's our partial. Those are our partials, and now I'm going to go over to that formula over there, right? And I'm just going to start plugging things in. I guess I have to erase this pretty drawing. So the directional derivative in the direction of the unit vector u of f of x, y should be equal to a, which is root 3 over 2, times the partial of f with respect to x, which was 3x squared minus 3y, plus the b, which was 1/2, right? And then minus 3x plus 8y. And that's it. That right there is the partial derivative, right? Sorry, the directional derivative of the function if I'm pointed in the direction of the unit vector u. And this will work for any point you give me now. So if I go to any point on the surface and point in the direction of u, this is going to be my tangent line. So now let's go to the specific point that we're talking about. which is the point 1, 2. So see, the 1, 2 really doesn't come in until the very end, right? And now this is just plug and chug, right? So 3 minus 6, I believe, plus 1/2, negative 3 plus 16. Check my math. I'm working fast here. Negative 3 root 3 over 2, and then over here, 13 plus 13/2. So negative 3 root 3 plus 13 over 2. Anyone else get that? Yeah? That's it. That's a number, right? And I'll get my calculator out just to see. I'm curious, like, is that a positive or a negative number? I guess we'd have to check, huh? Is it, this whole thing's 3.9, approximately? I'm trusting your calculator skills there. Can I get a second? Any 1 second? Not that I don't trust you, but I always like to have at least 2 people confirm. It's not that I don't trust you. It's I don't trust you. Sure. Yeah. It's less than 2, greater than 1. Yeah, yeah. I don't know. I don't have memorized. So, yeah, no. Yes, okay, so that's it. So that means if I were to be standing on that surface at that point up there, pointing in that direction, and take a step, I'm going to be going up, right? Now, if I turn around and go the opposite direction, what do you think is going to happen? If I turn around like 180 degrees? It's going to go down because, you know, if you're going up this way and you turn around, you're going to have to go down. So, all right. Questions?
If you have, could you draw the triangle? Could you draw a triangle just for my question?
You want me to just draw a triangle?
A random triangle. And then for your height, for 1. A right triangle.
Oh, okay. That's a spherical triangle. It's a triangle on a sphere. We'll talk about that later. So you mean like a Euclidean two-dimensional triangle, like this? I'm being a smartass, I'm sorry.
When I think of sine of 30 degrees, I think 1/2, and then I put 1 for the height, 2 for the hypotenuse.
Mm-hmm.
And then you can put root 3 for the, I guess, the x.
Yes, you could do like a right triangle like this and then say 1 and 2 and then root 3. Is that what you're saying?
Components, could you do root 3 and then 1 instead of root 3 over 2 and 1/2? Is that still a unit length?
Could you use what instead?
Saying to multiply everything by 2, basically.
You have to divide it by 2.
Could you,
Like,
could
would
you
that work?
use
Would that
root
use-
3
would that work for
and
you?
1
Could you-
as your u?
would that
No,
work?
that would not work.
It would.
No, because this is not a unit vector. Yep. So what you have to have, yeah, your hypotenuse would have to be 1. But what you could do real easily to fix that is just find the length of this vector. So, you know, find its length. Take the square root of each of these pieces squared. So square that, you get 3. Square that, you get 1. Square root of 4 is 2. And just divide each by 2. And now you have a unit. Well, that's what we had before, yes. So you would be off by a factor of 2 had you not normalized it and made it unit length. Got it? Okay, let's look at the next one. Or the next idea here. I shouldn't have been a smartass, I'm sorry. But it's interesting, you know, spherical triangles don't have the same properties that the ones we're used to have. All right, so z is equal to f of x is equal to natural log of x squared plus y squared. Find the directional derivative at the point 2, 1 in the direction of the vector u is 1, negative 2. So this is a little different in this problem because in the last one, told you that we gave you the direction by giving you an angle and how that angle was relative to the x-axis, right? This one, you're not given an angle. You're actually just given a direction vector, right? So I'm going to go back. I'm going to draw the domain again. The point that I'm at is 2, 1. The direction vector, which is completely separate from the point, right, has nothing to do with the point, is the vector negative 1, 2. Can y'all see the surface above this? Can y'all see the surface that's above this thing? And we're up at a point on this, and we just want to be on this surface pointed parallel to that red vector, right? And then you just turn the whole thing over, and now we're, the surface is up. Okay. So we need a couple of things: partial derivatives, which we should be able to take, right? And we need to figure out what our u is. U is given to us, or is it? It's not. It's not a unit vector. So we can't call that the u. Even though I called it u here, I'm trying to trick you. All right? So this is not a unit vector. So I'm going to call a new vector v, that u vector divided by its own length. And then what I'm going to do is in my formula, I'm going to use directional derivative in the direction of v, because v will be a unit vector. So we just take the vector u and then divide it by its own length. What is the length of u? Square root of 5, right? So I'm just going to divide it by its own length. But that just means you divide each of the components. And that's it. Yes, you could rationalize, but I'm just going to leave it like that. So this is a and b. We agree with that? All right, so I need some partials. Let me get some partials right now before I start putting this all together. Partial with respect to x. 2x over x squared plus y squared. So derivative natural log of something is 1 over it, and then, okay, partial with respect to y is 2y over x squared plus y squared. There we go. And now I'm ready to put it all together. So I'm kind of going a little quicker here with these partials because that's now in the past, okay? The directional derivative in the direction of v of the function at some point xy should be a, right? So negative 1 over root 5 times the partial with respect to x, which is this, 2x over x squared plus y squared, and then plus b, which is 2 over root 5, and then the partial of f with respect to y. Is it doing that again? I hear that every single time. See, I've got the magic stick. Is that what we called it last time? All right, so that's it. That's our formula, right? And then now we just need to plug in 2, 1, and we're done. So let's plug in 2, 1. Are there any questions? Does this seem straightforward? Yes? No? For now, I mean, we don't want to make this more complicated. The only thing that's going to get complicated perhaps in the homework is maybe these partials are going to suck a little bit. We haven't talked about yet, what happens if we have like a function of 3 variables. Like, can we still do a directional derivative? Does it even make sense? So we'll talk about that in a second. All right, what happens when I plug in 2, 1 for this right here? 4 over 5, 4/5. And then when I plug in 2, 1 on this one, what do I get? 2/5. And then adding these, they have the same denominator, don't they? Uh-oh.
Yeah, I got 0.
You got 0. Did we mess up? This is a number. It's not a vector. What does that mean? Flat. You're flat. So you're standing, and you might possibly be at the top of like a hill, or possibly the bottom of a hill, or neither one. It could be a saddle point. It could be a lot of different things, okay? Because the surfaces are complicated. It's not as simple as, back in Cal 1, your derivative in Cal 1, right? If the derivative was 0, you were either like here, right? Or you were here, or you could possibly have had something like this happen there, like this, right? Like that was pretty much it in Cal 1 when the derivative was 0. You were either at the top, at the bottom, or at one of these weird points like this where you're neither the top nor the bottom. This is kind of like what a saddle point is for us, which is later. But it can be even more complicated with surfaces. So it's okay to have a derivative of 0. The next section, in fact, is about trying to find the maximums and minimums of a function of two variables. It's a method, it's a procedure on how we do find the highest and lowest points on surfaces. And do you remember, like in Cal 1, we had like the first derivative test and the second derivative test? We have something like that for surfaces also. And then we say, hey, we can do a pretty good job with that. And then we get into the next section, which is 11.8, which is called Lagrange multipliers. And that's an even more specialized version of finding maximums and minimums. And that problem is, that section is kind of tough. But your test is a week from this upcoming Monday, right? Your midterm is a week after that. So we will have, next class we'll do 11.7, okay? And then we will, on Wednesday, do more 11.7, start 11.8. Then the following Monday will be your test. It'll only cover up through 11.7. I'm not going to test you on 11.8 until the final. All right? And maybe next Wednesday we'll have some time to talk about the midterm. Making a midterm is kind of hard because we have a lot of information, right? So how do I pick something that's going to fit in an hour, 40 minutes? I don't know. I guess that's the pleasure I get to have, is trying to pick something that fit in an hour, 40 minutes. And you have the pleasure of preparing for something that is going to be an hour and 40 minutes and can cover, almost 8 weeks of class. So it's a good thing. It's a good exercise because a lot of times as you get higher in your education, there's going to be less tests. It's going to be more like midterm final. I took plenty of classes where my grade was 50% midterm, 50% final. And for an hour, 40 minutes, you had to walk in there and perform. And you had to be ready for it. There wasn't any after the test like, hey, can we do corrections? Or like, can you curve us? Like, no, this is all grown up now. Okay, you just have to be prepared for that test. So, okay, we're done? This one? All right, so now we define something. We define what's called the gradient vector. This gradient vector is going to become very important to us as we proceed through this this chapter, and we'll see it again later on too. This is supposed to be a dot product. I don't know why that looks like that, but remember that this is the definition of the directional derivative, which is what I wrote up there on the board. If I were to create two vectors, a vector that the first component was the partial of f with respect to x, and the second component was this, and I dot that with the vector AB, then wouldn't this be equal to this formula right here? Because when you dot product, don't you do this times this plus this times this? Isn't that what you do when you do a dot product? I know it's been a while since we did dot products, but dot product was easier than cross product. So this right here is another way of writing the directional derivative, isn't it? And so this right here, we knew that this was the directional derivative, right? That was directional vector. That was the vector that told us which way to point, right? This we've never really seen before. We've never actually put the partials together into a vector, have we? Never. But now we are. We're going to put the two partials into a vector, and that vector is called the gradient vector. This right here is called the gradient vector. But this note is just to make you aware of the fact that you could rewrite this formula as a dot product. The next note is where we define the gradient vector. So the gradient vector is defined as follows, and that's what I wrote right here. This is, you've seen the delta before, right? Delta x, change in x, right? You've seen that before. Flip that delta over. That's the symbol we use for the for the gradient. And it's actually, this symbol is called del, okay? It's called del, which is also what I told you this symbol is called for the partial derivative. So same name for two different symbols. It's confusing, I understand. So del f, you'll hear me say del f, and that's what I'm referring to, all right? So just remember that the gradient vector is exactly that. It is a vector, and it's just made up of partial derivatives. That's all it is. Gradient vector is just a vector with the components being partial derivatives. So simple example, find the gradient vector. So this is one of those problems like someone who's never even ever seen calculus 3 or anything like that or any of this vector, they look at that, they're like, man, that looks hard. What's a gradient vector? It's nothing. It's really not much. It's just a couple of partial derivatives, right? Well, you know what I'm saying? It's not like, this is not going to be a 3-page problem. This is just an exercise in partial derivatives. That's all it is. So the gradient vector is this, right? And so let's just compute what's the partial of f with respect to x. Let's see. So what is we have a sum, right? So we can do partial of e to the x y with respect to x would be y e to the x y. See, I'm assuming that you're okay with that by now, all right? That you can do partial derivatives by now. Plus derivative cosine of x plus y. What's the partial of that with respect to x? Negative sine x plus y. Anything else there? That's it. Okay, I agree. And then now we do comma. So the second component of the gradient vector is the partial of that with respect to y. So it's instead of y e to the xy, it's x e to the xy. And then minus, this part's exactly the same. Okay, so if you are still at a point right now where this is like, what the heck's going on? Well, you've got work to do this weekend then. I think the take-home that I gave you, the partials get a little complicated because there's some product rule in there that you have to keep track of, and that's it. That's the gradient vector. Congratulations. All right. Now we're going to see the gradient vector is extremely important. We're going to see its value in a little while, but before we get to why it's so important, let's extend everything now. You know, everything we've been doing so far, it's been f is a function of two variables, x and y. And so we were looking at it as a surface. The domain was down on the ground, right, in two-dimensional space. But hey, what about if we have a function of 3 variables, f of x, y, z? Now your domain lives where? Where's your domain? The domain's in R3, right? Let's say someone gives you a unit vector in R3, which would be a direction to point in 3-dimensional space. Then the directional derivative, does this look familiar? This is exactly the formula before. I'm missing something. Do y'all see it? I'm missing all my z's. That's what happens when you copy paste. Hey, it was my own work. prove it, yeah. Okay, so the only difference between this and the one I put up on the board here is that because we have three variables, we're going to have three pieces, right? Three partials, partial with respect to x, y, and z. Each of these functions can be evaluated at an order triple x, y, z. And we'll have a, b, and then a third component of the unit vector. So everything straightforward, yeah? And then you could also break this apart as a dot product again. And we could call the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, put that into a vector, and we would call that the gradient vector for this function. So there's two different notations. Del f is either write it out that way with all the x, y, z's, that's too much, or just shorthand is something like that. Now this is something in the homework video I did this morning. I was trying to get this across in one of the examples, but I think I just made it clear. Hopefully it made sense that the problem that we started with, we had a point in the domain. We pointed out the first one we did, we pointed pi over 6, right? Then we went up on the surface, and here was the ground, and we were pointing out this direction, and we had some point out here, and we were trying to point parallel to it, right? And we got, if we walked out, what happened? We went up or down, right? That's what's happening when you have a function of two variables. But what if you have a function of three? Well, your domain is no longer this picture, right? Your domain actually is three-dimensional. The point that you pick instead of being like this is, some point in three-dimensional space. And the vector, the unit vector that you're pointing in, is actually a three-dimensional vector here, right? And so this point gets plugged into a function. I don't get to see that function. I can't visualize it. So it can't be me standing on a surface anymore. It's something else. So one of the clearest examples I can think of is imagine that this point lives in this room, right? And that's the temperature, right? And that's the one we keep going to, right? So then if I'm this point and I go start moving in a direction parallel to this red vector, so I start moving parallel, then what I want to know is as I move, how much does the temperature increase by? So the temperature is the output of this function. And so that would give me my instantaneous rate of change in temperature. Now I've been trying to put together a demonstration of this, a way to visualize a function like this, and I've almost got it done. What I've got is a point that's moving around in three-dimensional space that you can move, but I can't do temperature, right? So what it is right now is it's a green dot, and as you move around, it changes intensity. So it goes from like dark green to really light, like bright green. And so as you move around in space, like the function dictates the brightness of the dot. So the brightness of the dot's that output. It's a work in progress. I don't like what I have so far. So, okay, so what I'm getting at is with this, you cannot be talking about standing on a surface. Okay? We can only do that when the function is two variables. Can we actually visualize that? Why don't you work on this? See how long it takes you to get through this. You can talk to each other, right? This is not a quiz or anything. I just want to see what you do here. Can everyone read it? I'll make it a little bigger. So, that okay? Okay. Find the gradient vector. Then do the directional derivative at this point in that direction. Go ahead. I'll give you like 10 seconds? 10 minutes? 10 minutes. Progress or no?
Yes.
Yes? Got progress? All right. Let's see here. Anybody want to volunteer the gradient vector for me? Anybody feel good about their gradient vector?
I do, but I don't want to put myself out there.
Oh, come on. You can always just put or something if you want. Come on, go for it. I mean,
1 over y plus z
1 over y plus z.
and negative x over y plus z squared.
Y plus z
All of it squared.
squared.
And then the same thing.
Negative x again.
Yeah, negative x over y plus z squared.
Or y plus z squared. Okay, anybody agree? Got 1 agreeer, 2 agreeers, 3, 4. We got 4 people who agree.
Come on, guys. I thought we were friends. Is this how it's going to be? Okay.
So should I go through these, or I don't mind. You just got to let me know. Yes?
X in the first component.
Should be z. Yeah, thank you. This should be z. Thank you. I don't know if you probably said z. I just or something. Okay, so we agree with this now?
Yeah.
All right, so the first one is the easiest because you really have 1 over y plus z times x, right? On the first, like on this, right? That's what this is. And if I take derivative of that with respect to x, y and z are constants. That means this is a constant. Constant times x, derivative is just a constant. So that's this, right? Yeah? Now, if I want to take the partial of this with respect to y, x is a constant, so it's going to come along for the ride. So forget about that for now. But to do the derivative of this, because y appears in the denominator, you probably should move the y plus z up to the numerator, like that, and then take the derivative of this, which is chain rule. So negative 1 comes out, y plus z to the negative 2 times the derivative of what's inside with respect to y, which is 1 plus 0, because z is a constant. So just a 1 out here. But that's same as negative 1 over y plus z squared, right? But then you had the x. So x on top, so that's this. And then the other one with respect to z works exactly the same way. We good? Yeah? Okay. That's the gradient vector. Now what we need is the directional derivative at the point 411 in the direction of u. Did anyone get that part yet? So what did you do?
On the unit vector.
So you looked at the u and had to make sure it was a unit vector, which it wasn't, right? So you looked at u and realized it wasn't a unit vector, so you found its length. Square root of 1 plus 4 plus 9, which is root 14. And so I'm going to scale each of these components by this. I'll call that vector v is equal to 1 over root 14, 2 over root 14, 3 over root 14. And now it's just the formula, right? This is my a, b, and c. And so I'm going to take this vector and dot it with this vector, right? Take the v and dot it with this. So let's do that right here. What's the gradient dotted with v? It is 1 over root 14 times this plus 2 over root 14 times this plus 3 over root 14 times this, which gives us 1 over root 14 times 1 plus y, 1 over y plus z. And then this is going to be negative because that was minus 2 over root 14 times x over y plus z squared, and then finally minus 3 over root 14 times x over y plus z squared. And that's a number, isn't it? Dot products spit out numbers, don't they? Well, I have to give you x, y, and z, and then it'll spit a number out. But all right, so let's go ahead and I don't think I'm going to go through and plug everything in. Someone can tell me what the directional derivative in the direction of v of the function is at the point 4, 1, 1. What do you get?
Negative 1.2.
Negative 1.2? Anybody have the exact form, or is it real ugly?
Oh, it's negative 9 over 2.
It's negative 9 over 2 root 14? Anyone else get that? Yes? Okay, so all we do is replace x with 4, y with 1, z with 1 into this, and you should get this, which turns into this if we get on our calculator. So again, let's say that this function right here represented temperature in the room, and you're at the point 411, wherever that is, and you start moving in the direction of this vector, you start moving that way, the temperature is actually decreasing at that rate, negative 1.2 degrees. All right. All right, we're moving on. This is the most profound part of the entire class, this part right here. And this is the most important thing about the gradient vector up to this point. Is that if you were, go back, let's go to the surface because it's the easiest thing. You're standing on the surface, right? And you are up at some point, and you know that in each direction, right? In each direction, there's going to be some tangent line. The natural question would be, what direction do I point in to have the steepest tangent line, right? Like, where should I point so that when I take that step, I go up more than I would in any other direction? Does that seem like a very difficult question to answer? Yes or no? Does it seem like if you know the function that it's going to be easy or hard to be able to tell where to point and walk and that be the steepest? I mean, to me, that seems like a stretch. Like, we'd probably have to work pretty hard to get that information. But it turns out it's not hard at all. And it comes from the fact that we have a dot product. All right? So you go and you look at this. We are trying to figure out what will maximize the directional derivative. What will give us the largest directional derivative? Well, if we look at back from dot product way, way back when, the definition of the dot product, we had this alternative definition, right? Where as long as these weren't zero vectors, the dot product is equal to the magnitude of u times the magnitude of v times cosine of theta, where theta is the angle between the two vectors, right? And if we know that the directional derivative can be rewritten as a dot product, then we know that the directional derivative can also be transformed into this formula right here. Right? That's the directional derivative. Using the dot product formula, this is magnitude of f times magnitude of u cosine of theta. Right? Y is the next step here. U is a unit vector, right? So the magnitude of u should be 1. Yeah? So this formula turns into this. So the question now is, what will make this the biggest it can ever be? If this number right here is 1, right? Because cosine, the biggest it can be is 1. And the way that you get cosine to be 1 is by letting the angle be 0, right? Yes? That means that the angle, to get the biggest possible directional derivative, the angle between your gradient vector and the direction that you're pointing must be 0. So think about that. This is the profound statement. I'm up here and I'm like, okay, which way do I point? Which way do I point? Okay, let's call this u. That's the direction that I'm trying to point, right? And then I've got this gradient vector, which seems to have nothing to do with this, right? The gradient vector is the partial derivatives. and then someone's telling me to point in a direction. I'm saying, which way do I point so that I get steepest thing? Well, it turns out to get the steepest, you need the angle between these two vectors to be what? 0, which means that you must be pointing in the direction of the gradient. So the gradient vector itself is the direction that you should point to get your steepest descent. And that, to me, is amazing. All right? Because that means if you can calculate the gradient, then you know which way to point to get steepest descent. So this is the summary of it right here. Maximize the directional derivative. The maximum value of the directional derivative, the maximum value, is the magnitude of the gradient. The length of the gradient vector is the steepest slope you're ever going to have. And it occurs when we point in the direction of the gradient. Remember that. That's a big note right there. So here's an example. We have this function of two variables. First, let's find the direction as an angle of the maximum rate of change at 0, 0. So you've got some surface sitting up here, floating around here. It's not really floating. And you're at the origin, right? 0, 0. You go up to the function. Somewhere on the function you're standing there. And I'm asking you, which way do you point? Tell me which way you point so that you would get the maximum directional derivative. What do I have to do? I just have to find the gradient. That's all I have to do. Okay? So what's the gradient of f? Well, it's partial of that with respect to x, which is cosine x minus y minus sine x, right? So you have to do derivative of each of those, right? So derivative of sine of x minus y is cosine of x minus y. Derivative of the inside of this is just 1, plus the derivative of cosine x, which is negative sine x. So that gives you this. Then that's your partial with respect to x. Partial with respect to y is, be a little careful here, cosine of x minus y, but then derivative inside is what? Negative 1. So it's negative cosine of x minus y. And then derivative of this piece, 0, because x is a constant. So that's it, right? That's my gradient vector. All I need to do now is plug the point in. If I take the point 0, 0 into that, that will be the direction I should point, right? Because this is a vector. The vector gives me a direction. So cosine of 0 is 1. Sine of 0, 0, so there. Cosine of 0 is 1, but then negative, so negative 1. That's it right there. That's the direction I should point, right? So this goes back to like that domain picture. We were sitting here, we were at 0, 0, and then normally, like what I'd given you in the past, I told you what direction to point, right? I gave that to you. This question is asking which direction do I point for steepest descent or steepest rate of change. It's telling me to point here. So I point 1, negative 1, 1, negative 1. I point that way, and that's going to give me the steepest descent. I wanted it, though, as an angle, not as a vector. So what is that as an angle? So to answer this question, what is it? You say negative as an angle, not the point that you're at. Relative to the x-axis, right? That's the angle I should point. If I want to have the steepest ascent, what I need to do, standing at 0, 0, is I need to point negative 45 degrees, pi over 4.
Is it always relative to the x-axis?
You could make it relative to the y-axis, but then everyone would be like, why? Everything's always been relative to the x-axis, But you could. Just make sure you state it. That way there's no confusion. We good? That answers part A. What about part B? Find the maximum rate of change. So what is that maximum rate of change? It's the magnitude of that derivative. So all you have to do is take the magnitude of this. Square root 2? Root 2. Come on, this has got to be somewhat amazing. No, only to me, I guess. Only to me. You've got this surface. You're standing on it. You're trying to figure out where to go that you have the steepest descent. I can tell you which way to point, and I can tell you that's the steepest descent you're ever going to get. Root 2. That's it. You point in any other direction, it's going to be less. And it didn't take a whole lot of work for me to be able to tell you that. And then what I could do is I could move in that direction, right? I start moving in that direction, and I say the same thing at the next point I get to. And that would give me another direction, wouldn't it? And I keep doing that as I move, and eventually I'd be at the top, wouldn't I? And that's where you have, like these contour maps. If you look at a contour map, we talked about this last time. Contour map, works where each of these lines represents like an elevation. So maybe this is like sea level, 0 feet off the ground. This is like 10 feet. This is like 20. This is like 30, right? Then if you walk around a contour line, you never change altitude, do you? If you walk perpendicular to a contour line, you're walking in the direction of the gradient vector. That's what you're doing. And if you follow all, there's an infinite number of contour lines. We only show some of them. But if you follow all of the gradient vectors throughout the entire picture, then you'd start maybe down here. It would take you through, and it would take you up to the top of the hill. And that would actually be the shortest path up that hill, because it's the steepest descent. Right? Yes?
Can you explain one more time how we got negative for?
I'm just looking at this angle right here, relative to the x-axis. This is 1, -1. This is that vector. Yeah. Yeah, just using the fact that it's, triangle 1, 1. Yeah. So let's just say, just for the sake of demonstration, okay? Let's just say that we would have got something like this. This ought to be good. What if we got a gradient vector of -4, -7? What would the angle be? So you would come over here, and you'd be at -4, -7. You'd be down here, right? So you could make a triangle, couldn't you? You could make a triangle out of that? It would look like this. -4, -7. You're trying to find an angle here. So what would you do? Arctangent. You'd use the arctangent on your calculator. It's the arctangent of the y coordinate over the x coordinate. What would you get? Did you try it?
Yeah.
What did it spit out?
60.25.
60.25 degrees. So if you do arctan on your calculator of -4 over -7, what was it again? 60 point what? Oh, I just drew it wrong. -4 here and -7. Thank you. Yeah. Is that what you had done?
Yeah.
Okay, so what is it? 60?
60.25.
68?
No, 60.25.
60.25 degrees. Is that the correct answer?
No.
No, because that's actually just this angle. Your calculator doesn't know you're in the third quadrant. So you'd have to add 180 to that to put you over there. So you'd be a little careful with that. That would be, that's stuff from pre-cal though. We always have to be careful with that inverse function on the calculator, right? Those darn domain restrictions mess everything up. This problem is very similar to the one we just did. I think this one might be a little easier. Well, that's exactly the same, isn't it? Same instructions? Okay, so I'll let you do that on your own. I think that partials are easier on that one. Yeah? Ooh, now that one. Let's see about this one. Here's a function of 3 variables. Find the directional derivative at this point in this direction. So this is what we started class with. Directional derivative, I give you a vector. You've got to go through and make sure first that this is a unit vector, right? And then go through the whole computation. Then it says to find the magnitude of the gradient at the same point. So this directional derivative is giving you some instantaneous rate of change at that point, right? If we're pointing in a certain direction. This is also giving you an instantaneous rate of change at that same point. Which of those is going to be larger, A or B? B, it has to be. The gradient's always the biggest rate of change you're going to get. The magnitude of the gradient is always the biggest rate of change you're ever going to get. So, do you want me to work this? Yes? Okay. So let's do part A. I'm going to make this a little smaller. Or you know what? I'll go like this. There. So for part A, I need the directional derivative, right? The directional derivative in the direction of v of f of x, y, z should be equal to, why am I using this marker? Should be equal to a times the partial of f with respect to x at x, y, z plus b times partial of f with respect to y at x, y, z plus c times partial of f with respect to z at x, y, z. That's just the definition of the directional derivative. What are a, b, and c? Is it 1, 2, negative 1? No, that's not a unit vector. This is not a unit vector, is it? I have to make it a unit vector first, or else it's all going to be off. So what is the length of that vector? Root 6. So if I take this and I'll call it u. How about that? I'll just scale this 1 over root 6, 2 over root 6, negative 1 over root 6. Now that's a unit vector that points in the same direction as v. And so I should come over here and not call this v anymore, right? I should call this u. I was doing that intentionally. I wanted you to accidentally stumble into that, to remind you, you must make it a unit vector. Then I need partials. Are we going to do partials on that? That's going to be pretty easy, I think, hopefully. Let's see. Let's go ahead and start writing this down. A is 1 over root 6. And partial of f with respect to x is sine yz. Then I have plus b, which is 2 over root 6. And then partial of f with respect to y, which is x cosine yz times z. Right? Ignore the x, because it's a constant. What's derivative of sine of yz? Cosine yz. Then derivative of what's inside with respect to y? Z. So it's actually going to be xz cosine yz. Plus c, which is minus, so minus 1 over root 6. And now the derivative of this with respect to z. So xy cosine yz. Good. And now I'm going to plug in 130, right? So the directional derivative in the direction of u of the function at 130 is 1 over root 6 sine of, yes, sine of 0, right? Because z is 0. That's all gone, isn't it? Plus 2 over root 6. Yes, 0 again. Minus 1 over root 6. Right, this one's 0 because z is 0, right? Okay. This one, not so much, right? cosine, so 1 times y, which is 3. Cosine of 0 is 1, so 1. So this is just going to be negative 3 over root 6. Questions? No? Okay. Part B. What's the magnitude of the gradient vector at 1, 3, 0? Well, we know what the gradient vector is, right? We actually got the partials already. So let me just write down what the gradient vector is.
Wait.
Whoa.
For
What did I miss?
for this one, xz cosine 0, or cosine yz, shouldn't it be 2 root 6 there? Oh, z was 0.
Z was 0.
Okay, never mind then.
That saves us. That saved me.
Got it.
Yep.
Wait, no.
No,
Thank you.
no, I've made mistakes before. Wouldn't be the first time. Okay, magnitude of the gradient. So the gradient vector, I just erased it. Absolutely wonderful. The gradient vector,
That's why I said wait.
yeah. What was it? X sine yz? So sine yz, right? And then it was yz, and then xy, cosine yz. So that's the gradient vector right there, right? And all I need to do now is plug in the point 1, 3, 0. The gradient at 1, 3, 0 turned out to just be, well, this was 0, right? And this one was 0. And this one turned out to be 3, right? That's not the magnitude of the gradient, that's just the gradient. I need its magnitude to find the maximum rate of change. So the magnitude of the gradient of f, and this one's an easy one to do, right? But square root of all that square is just 3. So it definitely has to be bigger than the other answer. If this answer is smaller than the other one, something's wrong. All right? Good? All right, so tangent planes to surfaces. This is the last part of this section. So we already know, we've been exposed to the concept of the tangent plane. We did this, right? And the idea was this, I'll remind you since it's been, I don't know. Whoa. What we had before was this. We had that if z was equal to some function of x and y, that made a surface, right? That we could find the equation of the tangent plane to this surface using this formula. It was the partial of f with respect to x at x naught, y naught, x minus x naught, plus partial of y, f with respect to y at x naught, y naught, y minus y naught, minus 1, z minus z naught equals 0. Do you remember that? It just said that, look, the A, the B, and the C for the standard form of a plane, right? We had ABC. The ABC is the direction vector. That this A and B came from these partials. And the C I told you was always -1. Didn't I? But what we needed for this to work is that we needed z to be a function of x and y so that you could draw a surface. Now what we're going to do is we're going to generalize this even further. Do y'all recall this? I mean, we did do this in class. We're going to generalize this formula, and this time we will no longer need the condition that you can solve for z. You no longer need that z is a function of x and y. Now you just have an equation, any equation that connects x, y, and z together. So if you give me an equation that's x, y, and z are all in the equation, then I can find the equation of the tangent plane to any point on that surface using this formula right here. Does it look familiar? Yes. Now, we've got three variables, right? X, y, and z. So you have to give me a point on the surface, x naught, y naught, z naught. Because this surface could possibly be like, an ellipsoid, a ball, like a sphere. So you could have points on the top and the bottom. It's no longer a function of x and y. So you have to give me exactly where you are on this surface. Give me that point, that's x naught, y naught, z naught. And then what I'm going to do is this part, and this part. That's that standard part of the equation of a plane that we've seen so many times before. X minus x naught, y minus y naught, z minus z naught, right? But these pieces are now a little different. Partial with respect to x, that's the way it was before, wasn't it? In the previous tangent plane equation. Partial with respect to y, that's what it was before. The difference, though, remember that was -1? No longer -1. It's this. It's the partial of, with respect to z. So this is the a, the b, and the c. So that's actually the normal vector of the plane. Remember the normal vector sticks out the plane like this? So the gradient vector is the normal vector of the plane. That's what it is. All right, let's see if we can do one of these. I've got a little bit of time. Find the equation of the tangent plane to this ellipsoid. Now, you may or may not recognize that as an ellipsoid. We talked about quadratic surfaces at some point in this class. We wanted to be able to recognize them. And I said, hey, let's not try and memorize them. Just remember, they're all on that one page, and you could look them up. But this is an ellipsoid. I'm telling you that. So you got this ellipsoid. Looks like an egg, right? And we're going to some point on it, wherever, -3, 4, 5, wherever that is. And we're trying to find the equation of the plane that is tangent to that ellipsoid. That's what we're doing. Got it? So what we're going to do is first take the equation, move everything to one side, which it almost already is. If this is a constant right here, you actually don't even need to move it over. It'll still work. And I think in the homework problem I did, I just didn't even move the constant over. The reason why it won't matter is because you're going to take a derivative of that, and that constant's always going to go away. This left side, though, of this equation is capital F of x, y, z. That's the thing we're going to take partials of. What part of the equation of the plane, what part of it can you tell me right now without doing any of the work?
X minus x.
You can tell me x minus x naught. So I know x minus x naught, so x plus 3. Then there's something, then it's what? Y minus 4, and then I know it's z minus 5, and I know equals 0, right? That much I know. Just a matter of figuring out what these numbers are in front. Those numbers are the direction numbers of the normal vector, but that comes from the gradient. So just some partials now. What is the partial of capital F of x? Or sorry, the partial of capital F with respect to x would be, oh man, that's cake, right? 2/9 x. And partials don't get any easier than that, right? Well, I guess they could, but not much. Partial of f with respect to y would be 2y. Partial of f with respect to z, 2/25 z, right? Man, that's nice. And now what I need to do, this one, this number right here, is a partial of f with respect to x with -3, 4, and 5 plugged into it, right? So plug in -3 for x, 4 for y, 5 for z. But it only has x in it, right? So all I have to do is plug in -3. Let's plug -3 in right there. What do you get? -2/3. So this is -2/3. Then I need to do this one, which is the partial with respect to y at the same point. Fortunately for us, this only has y in it. So I just plug in 4, and 4 times 2 is 8. So this is +8. You following? Last one? 2/5. Voila, there it is. That's the equation of the plane. Now you could go through and clean that up, right? Distribute through. If you didn't like the fractions, you could multiply both sides by 15, and you could do whatever. I've seen on your homework, on your homework, I meant on your take-homes, I see some of you leave them, some of you clean them up. I don't care. It's all the same, right? It's all the same sheet of paper on, living in three-dimensional space. So, not bad, huh? Not bad? Questions? Questions? I've got something interesting to show you. No questions? I can erase?
Do you need it first?
Wait, hold on. Nope. Messing with me. We said that if z was a function of x and y, that the formula for this, for the equation of the tangent plane, right? We said the formula was partial of f with respect to x at x naught, y naught, times x minus x naught. Then it was plus partial of f with respect to y at x naught, y naught, y minus y naught. This is the second time I've written this on the board today. And then it was what? Minus 1, and then z minus z naught, right? Equals 0. That's what we said, right? And I just told you that, and you believed it and everything. And I told you it was always -1, right? It was always -1. I told you that. Okay, so what I'd like to do now is I'd like to imagine that this is an equation, right, that does involve x, y, and z, doesn't it? I mean, I'm not telling you what f of x, y is, but would you agree that we should have x, y's, and z's in that? I'm going to use the method we just did to prove that this formula is right. So what I'm going to do is move everything to one side first. And I actually think I'm going to bring the z this way. So this is 0 equals f of x, y minus z. Right? This right side is capital F. According to the formula, x minus x naught, I know. Y minus y naught, I know. Z minus z naught, I know, right? Equals 0. I just have to figure out what these pieces are. What is the partial of capital F with respect to x? Well, what's the partial of this with respect to x? Well, little f. Partial of little f, right? With respect to x, that's what that is. Then you could say at the point, you could put here x naught, y naught. Z naught, I don't have to worry about. Why don't I have to worry about z naught into this piece right here? It just has x's and y's, right? There is no z in here. So this is just going to be partial of f with respect to x at x naught, y naught. And then minus what's the derivative of z with respect to x? 0. So that's it. Then I get to this piece. What's the partial of capital F with respect to y? Well, it's the partial of this with respect to y at x naught, y naught, right? Minus the partial of z with respect to y, which is 0. Okay, move on. Here, what's the partial of this with respect to z? It has no z's in it. That's a function of x and y, so it's 0. What's the partial of this with respect to z? -1. There it is. So that formula actually came more from this one. Like the one I gave you just today did not come from that one. It was the other way around. That one comes from this one. No, that one. That one comes from the previous note. Got it? Okay. One more thing to talk about. Was that the same problem? Yes, that's the same problem. Look at the directions. These are a little bit different than what we just did. Find the equation of the normal line to the tangent plane of the ellipsoid. So we have the same picture we just did a second ago. We had an ellipsoid. We picked a point. We found the tangent plane. And we got that, didn't we? We got the tangent plane. Now what we want is for you to take that plane, right there, okay? Take that plane and give me the equation of the line that is normal to the plane. Now what we mean by that is the line that is perpendicular to the plane, that pops out of the plane, normal meaning perpendicular. So what's the equation of this line? Well, what do you need for the equation of a line? A point and a direction vector. Do we have a point? Yes. Do we have a direction vector? What?
It was -2/3.
It's the normal vector of the plane, which is the gradient vector, right? So this is really just, once you've answered the previous problem, this problem falls out immediately from it. So we were trying to find the line that comes out of this thing perpendicular to that plane. That's what we're trying to find. This line that extends in both directions forever. That's called the normal line. So for that line, what did we use for lines? I forgot what we used for lines. R of t. Thank you. R of t equals R naught plus TV. Remember that? R naught is a vector that you create from any point on the line, which we want the normal line to go through that point. So that's going to be -3, 4, and 5, plus t times v is the direction of the line, which we said is basically parallel to the normal of the plane. I forgot what the normal of the plane was. -2/3. 8. 2/5. That's just the A, B, and C from the equation of the plane. And then you could put those together, right? Put these two vectors together. I won't do it. We've done that before. You could then you could say, okay, this is the vector equation. You could be asked to write it as the parametric equations. You could be asked to write it as the symmetric equations. I believe that's the end. Oh, that's just a picture. There it is. That's the actual ellipsoid we were just looking at. I think my picture was actually better than this. Don't you think my picture's better than that one? I think it is. There we go. That's the homework. All right. Hey, a little bit of, I guess, a warning. I don't know if this is that's the right word. I get the sense that a lot of you are a little bogged down with all your other classes, and you're bogged down with these mini exams, and they're really you're focusing a lot of time and energy on them. And that's great. This midterm is going to be focused solely on homework problems. And so I get a sense that there are a lot of people who are just doing mini exams and aren't really touching the homework. And I just don't want that to come back and bite you, because you need to at least expose yourself to the types of problems that you're going to be asked on the test. So make sure you take some time to get yourself up to speed, caught up on all the homework assignments. You don't want that to be 11 o'clock the night before, right? that you're like, I'm just going to go back and review all this homework. The expectation is that you've been doing the homework and the mini exams. That's the expectation. So, yes?
Is the midterm gonna be more like the mini exams or
I thought I just said that. Well, no, I just did. Did I not make that clear? I'll make it more clear. Just it's going to be over homework. I mean, that's what I'm concerned about. Is everyone's like, yeah, I've been kicking ass on these mini exams. I'm doing a good job, and like I'm getting the hang of this. And then you get to the midterm, you're like, what the hell's this? Oh, that's the homework you were supposed to be doing. Like you don't remember seeing a problem like that? So focus on homework for midterm. Yes. Yeah, and examples that I do in class. Yeah, what you'll notice though is a lot of the examples that I do in class are just the concept. Okay, so like the problem we just did, like this tangent plane one. The partial derivatives were pretty easy. In the homework, they get a little bit tougher. And so, yes, I would say always go back and look at these notes, these examples. But also go to your homework and find like, okay, he did one like that in the notes. Here is that example in the homework, but harder. Make sure you know how to do that. Any other questions? Okay, have a great weekend, right? It's Wednesday? Have a great weekend. Not really. Yeah, there's really not going to be a review for the test. It's just practice your homework. Yes. Huh?
Before it, I would say performance.
I haven't decided on that. Let's talk.